Assistant Professor Dr. Niti Yawanit and audiences. Today we would like to present about the effect of magnesium doping in zinc oxide buffer layer on zinc oxide thin film device for electronic applications. Members of our team are Mr. จิรพันธ์ผินกระโทก ตนุพันธ์แซ่ลิ้ม ปณชัยทองยอดเกลือง วงศกร รัศพร พลหาร สุริมาศ ณ ปางช้าง สุพิญญา เจืองสอน and my name is เพชรพนิษฐ์ นิ่มกิ่งรัตน์ We are a senior studying a major in advanced material and nanotechnology. All we want to present today is starting with introduction, following by experimental and detailed results and discussion, and the last one is conclusion. Let's start with introduction. I would like all of you to know what zinc oxide is. Zinc oxide is the one metal oxide semiconductor that always used for electronic application, such as light emitting diode, solar cell, and sensor. Zinc oxide has a wide band gap of 3.4 electron volt and a large exciton binding energy, which make it a better ultraviolet emitting efficiency at low temperature. Zinc oxide can be deposited at low temperature on substrates, cheap and non-toxic. Moreover, it has a high optical transparency, high conductivity, and stability under hydrogen environment. It also exhibits a self-organized growth property that enables easy formation of zinc oxide nanostructure on a variety of substrates. From all that point, it always desirable to grow good quality of thin films. However, the growth of zinc oxide thin film on silicon substrate is concerned because of the large lattice mismatch. It can be overcome by using an either approximate substrate. Previous work demonstrates that the optical property also get improved with the inclusion of buffer layer, and quality of zinc oxide thin film can also be controlled by the varying the thickness of buffer layer.
Magnesium is an element used in zinc oxide because of the wide band gap. As a result, the energy band gap of zinc oxide more than 3.37 electron volt. An atom of magnesium can be easily dissolved in a tetrahedral void of both sides as well because of therefore, magnesium is used to improve the structure without losing the oversized structure. And this is the figure of oversized zinc band, zinc oxide, magnesium oxide, and magnesium zinc oxide structure. Why magnesium zinc oxide layer was formed? Because it can stay the zinc oxide structure, and magnesium can cause further zinc oxide coating. So, the research is to study the amount of magnesium that can improve the base property. Next, in part of experimental and detail. Step 1. Wafer cleaning. Preparation RCA1 and RCA2 are composed that follow. Heating solution RCA1 and RCA2 and dipping the wafer into RCA1 and RCA2 in 15 minutes. Dipping the wafer into SF acid and DI water, and last, rinse with water. Step 2. Preparation of target materials. There are two types. Type 1, buffer layer magnesium zinc oxide. Type 2, zinc oxide, preparation of zinc oxide thin film. In type 1, preparation of buffer layer magnesium zinc oxide. Ingredients include zinc oxide, magnesium oxide, and PVA binder, and mill in 3 hours, and hydraulic press to pellet and sintering. In type 2, preparation of zinc oxide thin film. Ingredients include zinc oxide and PVA binder, and mill in 3 hours, and hydraulic press to pellet and sintering. Step 3. Deposition of zinc oxide buffer layer. This process is called with high vacuum. The silicon wafer is substrate and the magnesium zinc oxide is target. After that, heating the magnesium zinc oxide with a tungsten filament, resulting in the diffusion of magnesium through the coating on the substrate. The coating has a thickness 100 nanometer, measured by DTM digital thickness monitor, and hot buffer furnace for 1 hour, and was annealed at 773 Kelvin and cooled down to room temperature.
Okay. Step 4. Deposition of single-side in film. After the magnesium single-side buffer layer, the active single-side in film will go on buffer layer by radio frequency magneton sputtering using the single-side packet. The chamber was evacuated to a vacuum level of 10 to the minus 6 millibar. Feed oxygen and argon gas with a high validity. The argon gas oxygen ratio was set at 10 per 40 SCCM. The flow rate of oxygen gas and argon gas controlled by manifold controller. The RF power applied to the target was maintained at 300 watts. The deposition time was set at 1 hour. So, the thickness of the deposit film was approximately 600 nanometers. The sample were again annealed at 773 Kelvin to get better quality of single-side in film. The deposit single-side magnesium single-side p-type silicon sample were then left to cool to room temperature before carrying out the structural and optical measurement. Step 5. Preparation of Schottky and ohmic contact. Step 5.1. Schottky contact. The Schottky contact on single-side antenna reformed by using the metal with a high work function. In the present, using gold palladium alloy. The dot have been evaporated on the top of the vertically aligned single-sided film using the shadow martin nuclear to form Schottky contact. The diameter of the gold palladium target was 50 mm and deposited on the single-side thin film by using sputter coater unit. The Schottky contact are 17.85 cos 10 to the minus 3 square meter. So, add to form a large area contact on single-side thin film under it. Step 5.2. Ohmic contact. Aluminum was also deposited on the thin film using the same shadow mark. By RF sputtering setup, you need to provide ohmic contact to the device. The figure shows Schottky contact and ohmic contact. The next is result and discussion. Thank you.
The next is results and discussion. In XRD analysis, XRD was used to study the crystal structure of the magnesium single-side buffer layer and single-side thin films. This is XRD image of magnesium single-side buffer layer. Has strongest peak at 002 plane direction, illustrating that the planes are preferably oriented towards the axis. Single-side peak is strongest up to 3 atomic percent. After this, the intensity. Magnesium peak starts dominating single-side peak due to aggressive doping. This is XRD image of single-side thin films. Has strongest peak at 3 atomic percent. At lower 3 atomic percent, no magnesium peak, but at higher 3 atomic percent, magnesium peak is occurring. Sharp XRD peak refers to hexagonal oversized structure. In all cases of the single-side thin films are strongly Z-axis oriented toward 002 plane direction because it has lower surface energy in the single-side crystal. As the film grows, the grains which acquire lower surface energy become larger in size. The left picture is showing hexagonal oversized structure and the right picture showing growing Z-axis oriented along the 002 plane direction. XRD peak shift to lower value of 2 theta with increasing magnesium up to 3 atomic percent and shift to higher when more than 3 atomic percent of magnesium. The radius of the magnesium ion is smaller than the zinc ion. It is very easy to substitute the magnesium ion in place of zinc side. When magnesium up to 3 atomic percent, the fluid at half maximum of 0 to 10 peak will decrease, while 4 to 5%, the fluid of half maximum of peak starting increases. When increasing of magnesium, the 101 peak starts dominating because of incorporation of the magnesium in the interstitial side of the single side lattice. In this slide show in equation to calculate the lattice constant, crystallized site and strain in the single side thin films. In this slide show structural parameter of magnesium single side per layer in table 1 and single side thin films in table 2 are calculated by equation from previous slide. Both table 1 and 2 at magnesium concentration up to 3 atomic percent, the fluid at half maximum interplanar spacing and strain decrease, while the crystallized site increases. From table 1 and 2, magnesium single side per layer improve the crystalline of single side film. Increment of magnesium in magnesium single side alloy linked to merging of hexagonal and cubic phase. Cubic phase of magnesium single side causes the degradation of the crystallinity of the single side thin films, and lattice mismatch between single side and magnesium single side linked to misfit dislocations and stacking faults. The next is EDX analysis.
Next, this slide presents the result of EDX analysis of zinc oxide thin film on silicon substrate. In terms of quantity, we will find an atomic percent of zinc, silicon, oxide, and magnesium. The high peak will show the large quantity of elemental. The dose of magnesium is better because it shows up with high percentage. This picture shows effect of magnesium on zinc oxide thin film. The large gain of the doped zinc oxide film increase with increase in magnesium concentration from 0 to 3%. At 3 atomic percent, have hexagonal shape with perfect C-acid orientation, and then decrease with further increase in 4 to 5% of magnesium concentration because of the large mismatch. Because of the large acid mismatch in between zinc oxide thin film and buffer layer. With magnesium atomic percent, zinc oxide could be better candidate for UV detection and gas sensing application. This is attributed to the phase deterioration and large gain go on silicon solid and large gain go on the surface of zinc oxide thin film.
And next is AFM analysis. This technique used for studying roughness and morphology of thin films that divide into two parts. The first one is buffer layer. This slide shows surface of buffer layer with different magnesium content. The rough surface becomes to smooth surface when magnesium content increased from 0 to 3%. But when magnesium content increased over 3%, smooth surface becomes to rough again. And at the same time, in zinc oxide film that have evolution like buffer layer, when magnesium content increased from 0 to 3%, rough surface of zinc oxide film will smooth and grain size of polycrystalline zinc oxide increase too. But when magnesium content increase more than 3%, surface and grain size will rough and smaller. And next, this table refers to parameters from AFM analysis that represent differentiation of grain size and roughness when increasing in magnesium content. It can be concluded that the surface roughness of film depends on the type of buffer layer, and grain size of zinc oxide increase with increasing magnesium. And if excessive doping magnesium causing roughness increase again because phase deterioration and large gain coalescence on surface of film. And next, the optical characterization. These figures show reflectance and wavelength of thin film with different magnesium doping. Reflectance decrease with increasing magnesium and increase again when magnesium content is over critical concentration of 3%. And next, the formula for calculate optical band gap, or can estimate by relation between formula in y-axis and photon energy. On this graph, 3% magnesium have the highest band gap energy because reduction of defect in oxygen and zinc interstitials. This behavior can be explained by the zinc is n-type semiconductor, so the Fermi level is close to conduction band. When doped heavily magnesium, it causes a large number of free electrons at a result band tail which have Fermi level inside. It can be concluded that the band tail cause reducing in energy of band gap. The thin films can absorb in longer wavelengths because it is lower energy. So the absorption of film can improve by adjusting magnesium content.
The next topic is theoretical characterization. At the left side of this figure show the Schottky contact, and this figure show the talent voltage characteristics of 0 to 5 atomic percent of magnesium zinc oxide buffer layer. All these characteristics show about the rectifying behavior of the device, and magnesium zinc oxide buffer layer reduces the ionized carrier concentration by modifying of the surface of thin films. Next. The first equation used to calculate the identity factor, and the second equation used to calculate the barrier height. The series resistance of substrate materials is mainly responsible for the concave curvature of flowers by at high voltage, and can calculate the resistance by this equation. This table contains with the theoretical parameters, the barrier height, identity factor, and the series resistance decrease up to 3 atomic percent and increase with increasing of magnesium concentration. On the other hand, the rectification ratio and reverse saturation current first increase with increasing of magnesium concentration up to 3 atomic percent. Then for the 4 and 5 atomic percent of magnesium is decreased. Zinc oxide thin film doped with 3 atomic percent of magnesium has the low risk, the barrier height, identity factor, and series resistance, but rectification ratio is highest. So the best quality Schottky contact of film is zinc oxide thin film doped with 3 atomic percent of magnesium. The superior theoretical property of zinc oxide thin film doped with 3 atomic percent of magnesium because it has the better of crystalline nature and structural properties, and has a superior interface between the Schottky contact and thin films. For zinc oxide thin film doped with 4 and 5 atomic percent of magnesium, the property degrades because magnesium ions occupying oxygen interstitial site, which should cast electron traps. This result affect the interface state through first reduction of charge carrier and induction of carrier trapping.
And the last one is conclusion. In the concentration of magnesium at 3 atomic percent give us an excellent crystalline nature, morphology, and photography of the surface electrical and optical property of zinc oxide thin film. The electrical property revealed that the device had good rectifying. With magnesium 3 atomic percent of zinc oxide buffer layer, exhibit the optimized result and can be deployed in many electronic and optoelectronic applications. Thank you.